please, attention, attention. All luggage not attended by anyone is going to be destroyed and shipped to the field at headquarters. Anyone here suspecting this speech being English? Okay, you got me. Yeah, welcome to the first Camp FieldNet speech. Thanks to the CCC that we're actually allowed to talk here. What we're doing, if this laptop's going to not stop to the server, just what about the next slide? Damn it. Okay. So this is today's session. We're talking about stuff Cisco fucked up in the past, in the present, and stuff they're going to fuck up in the future. So we're covering pretty much all the Cisco bugs and advisories they came out with since their existence of PCERT. And we're going to go into some of them in a bit more detail. We will cover some of the rumors that are around for quite a while about Cisco hacking. We talk about the present, what's going on right now, basically what are we doing. And we're talking about the future, what we expect to go wrong. The beginning, actually the first advisory Cisco published, funny enough, was about a security feature. It was about their access control lists. Access control lists, for those of you who don't know Cisco that well, are actually used kind of like IP chains, IP tables, for non-stateful packet filtering. And so they got a keyword there that's called established that basically matches all packets TCP that contain an acknowledge or reset flag. So they consider this being part of the communication. So what's not covered in established, of course, is the SYN flag. So what they do is they say, well, if there is something with a SYN flag that's not established, that's a new connection, let's take a different rule. The first bug they ever published was actually a bug with the established keyword in certain series of routers. They had the problem that even SYN packets were matched by the established tool and therefore permitted instead of dropped. And the problem here was that new technology in the Cisco routers, namely the MCI, SCI, and CBus interfaces, I actually only know the CBus, use that. They basically forwarded packets directly from one interface to another without asking the CPU. And well, the CPU didn't see the packets, so it couldn't apply access control lists, and therefore you could pass by the firewall. Beginning number two, pretty much the same effect. Your access control list doesn't work the way it is expected to work. Was the so-called TACXDS bug. They had a keyword, TACXDS, and everyone running Cisco iOS and updating it once in a while knows that you take the iOS, you update it, you boot the router again, and it's going to complain about your config all over the place because they renamed stuff, they moved stuff from one section to another and whatnot. And so this is what happened here. They renamed the keyword TACXDS to TACX. Now, when the router loaded this line in the access control list and say TACXDS, I don't know what the shit that's going to be, so I just ignored the line. Which means this line was actually supposed to say every time you connect to the router or you pass traffic through the router, it's going to validate that you're supposed to do that with the TACX server. So now it didn't do that, which means, well, you're allowed through depending on the configuration. And so the thing is that the config keyword discrepancies between different iOS versions are quite well known. But here we got the fact that the discrepancies between the iOS version parsing of the protocols actually caused a security issue. That was the first time this happened. It wasn't the last. More iOS bugs. We got a bunch of slides on that one. The next one, chronologically, was interesting enough. 2 years later, so 2 years, they had no security issues at all. Was the Cisco PPP SHAP bypass bug. We never had really the information published on what the bug exactly was. So if someone knows, please hook me up on that and tell me. The thing was, it was a 10 series iOS, and what happened is if you do a PGP connection to one of those devices and it's asking you for shell authentication, you could actually bypass the whole shell authentication thing and just get an IP address and get online without authenticating. The suspected attack vector is actually PGP vendor-specific extensions. Now the next thing, some months later, was the LAND attack that was pretty much well known to everyone doing TCP/IP stacks at this time. If you remember, the LAND attack was sending a SYN packet with the source and destination IP address being the same and the source and destination port being the same, basically causing the TCP/IP stack to send a reset to its own port. And then, well, it gets a reset and it thinks, well, this reset is not what I suspected, so I sent back a reset and it basically killed itself. So Cisco, of course, doing TCP/IP stacks, of course, did the mistake as everyone else did. And even the new, at this time, brand new CAN-OS for the Catalyst switches was affected, so they didn't start recoding the whole thing, but they just took basic functionality of iOS and put it into CAN-OS. Even more iOS bugs. The AAA bug. Cisco has some pretty interesting naming convention. AAA basically is everything that you would consider authentication. Everything else that Cisco does is basically just asking you for a password. So AAA means talk back to attack server, have username and passwords, talk to radios, whatnot. What happened here, January 98, is that the answer from the attack service, the packets didn't get reassembled correctly, so the process didn't get the full response, which means in the header of the response from attack server, it says, yes, the user is okay. But in the remaining packet that the process never saw, it said, well, this user is okay, but please prevent it from doing this, that, and that. They didn't get the second part, so you got full access. The next thing, also details never released, same year, August 98, was the VTI login bug. Apparently, what the customers called up Cisco and said, look, we got those strange little crashes on the backbone routers, and that's really bad for our routing infrastructure, and it's like puking all over itself. So could you find out what it is? And after a while of tracking, they figured script kiddies actually were tallining to their boxes, entering some weird number of characters, and the box just crashed. So this is why they finally came up with a fix and actually released an advisory on it, but also, again, never released details. The history bugs, actually quite well known. October 98, I actually met the guy at CanSecWest, but I had to promise him to not disclose who he is. He said he was actually playing around with his Cisco and he was like bored shitless and stoned out of his head. And so he was like typing away on a keyboard and happened to see commands that someone else on the Cisco router had issued when he was logged in, right at the login prompt. So you basically tell to the router, it tells you to log in, you press the funny number of characters, actually it's 4 key combinations, and you see the command someone else issued on the router when he was logged in last time. Which is pretty good because people tend to like configure passwords that way. And it yields some interesting information. The Cisco advisory on the other side actually talks about a trusted customer doing that, and he found that in a lab test. I actually wonder how many people knew about that before Cisco did. Anyway, the next one was access lists again. This time was the 7000 series routers. Distributed fast switching is one of the, I guess it's about 5 different ways the Cisco can forward packets. The easiest way is called process switching. That's pretty much what your Linux system does, like copy the packet into RAM, tell the process to forward the packet, the process figures out where to forward the packet, puts it on the interface, sends it out again. Takes a shitload of time. And so they came up with new, improved technologies on doing that. And the 7K series had the distributed fast switching. And this one, same issue here. They started to implement a technology that increased the packet forwarding rates, but they actually totally forgot about matching it with the ACLs. So again, your access list wouldn't work. And it's pretty much the same problem we had in 95 with the established bug. It's the same thing. You've got a new technology that shortens the path of a packet through the router, and those people are engineers that are supposed to figure out how to get a packet as fast as possible from A to B. They're not supposed to think about how to get a packet from A to B and check all the features we got. This is not their job, so they don't care about it. Then we got a pretty interesting thing, and so far nobody at Cisco was able or willing to tell me where this actually caused. It's the so-called net leak bug. Basically, if you had a network address translation set up on your Cisco router, and you forward packets through it, it will actually leak packets to interfaces. It was not supposed to do that, and it will actually, at some point in time, leak packets that you send to the net device, and the net device from the outside wouldn't even be able to figure out which computer on the inside to send it to, which is the basic problem of that. They would actually take the packet and just pass it on the wire inside. It was pretty funny because, first of all, 12.0 was out at this time, so the new 12.0 main line was affected as well. We see a pattern here. And it's again said to be found with customer testing. Interesting enough is, the advisory updated, I guess, a year ago or something, still says they have absolutely no idea where this comes from and how to trigger that. It just happens. And they changed stuff on the code, and, well, they don't really know what they changed. Interesting enough, 4 years after the first advisory, someone at Cisco figured out that the biggest routers they got, the GSR 12000 series, has the same problem. Congratulations, that is impressive speed. You're pretty much as fast as the Work project. I'm sorry. It's like, I mean, you got this bug in all your routers. What about like taking the problem and testing it with all the others? It's not so hard to think about it. Yeah, it's the exact same problem, actually exact same switching method as well, just with a bigger router. Took them 4 years. Even more iOS bugs. Now they introduced HTTP daemons. Now if you actually happen to be at the last CCC Congress, we were talking about different embedded systems having bugs in the HTTP implementation. The funny thing is here, so far I don't have anyone who can prove me that I'm wrong with my rules, saying if you've got an embedded system and port 80 TCP is open, it is vulnerable. What happened with Cisco is the same thing. They introduced an HTTP daemon for easier configuration. Actually, it sucks so badly nobody's using it. But of course, when they introduced the HTTP daemon, they introduced bugs. The first bug that was discovered, May 2000, was the double person bug. You know, HTTP encoding percent AB being whatever character, AB is an X. And so if you got like 2 person sign, it would go into an infinite loop. And well, being the Cisco iOS that you can imagine as one fucking big MS-DOS program running off your disk, it will actually die on the infinite loop. Now the thing is, I happen to not know about this bug. I found it about several months ago with a different way to trigger it. So it didn't even match the iOS versions that are supposed to be fixed and not fixed. Obviously, there's way more stuff with the HTTP encoding in the iOS than we know. The next one, of course, being, again, HTTP. Welcome, you just created a perfect tag vector on your Cisco device. When you do device whatever / whatever / it will freeze. Same problem here, infinite loop. It obviously thinks it's still a URL, but matches the question mark before and figures this is CGI variables. And interesting enough, they actually published a big advisory on it and say this is dangerous, limit access to your HTTP whatsoever, despite the fact that you need the enable password to do that. Well, if you got the enable password, the last thing the actually official owner of the device has to worry about is you accessing the HTTP and crashing the device. Next thing, Snmp all over the place. Of course, pretty well known is ILMI. The ILMI community, they introduced for ATM switches. Unfortunately, their code maintenance is so crappy that they had the community hard-coded in every single iOS they put out. And then, of course, we had more Snmp beginning 2001. Another same issue here, community that was supposed to be just for cable modems, put into every single device, or actually every single iOS version they put out, cable DOCSIS. And then we got the read-write community visible, same problem, HP still has it every single device they ship out. You do an Snmp walk with the read community on the device, and some undocumented OID will tell you what the Snmp write community is. Not considered a brilliant move. And of course, the same thing, Snmp trap. You set up Snmp trap. The trap is supposed to have a community with it. You set it up on a Cisco, and it would actually allow this community also to do read-write, just to make things simple for you. Then, one thing that I really find very amusing is the PPT debug. Now, according to the advisory, it is just a malformed PPTP communication to the device, which is correct. And it will deny of service the device, which is also correct. It is also the first advisory they actually gave credit. If you watch the numbers, it took them 6 years to figure out how this credit thing works. And what I find interesting is, according to some people at Cisco I talked to, what they did was they implemented PPTP so it would work with Microsoft. Now, if you remember, the PPTP bug was actually found on Microsoft Windows. What they did was correctly reproducing the way Microsoft PPTP worked, up to the point where the bug happened. Congratulations, great portability. The big HTTP thing, I guess pretty much 80% here in the room know about it. It's known as the exec level bug. It works, as described here, device address, level, and then 16 to something 99 exec. It's on HTTP and you get full enable access over the HTTP interface. The advisory still says, today, no malicious exploitation of this vulnerability is known. I know different. I don't know how it is with you, but I know so many people that own a 4-digit number Cisco's in the internet just because they got 11 series iOS on it in HTTP. And then of course, malformed Snmp February 2002. Simply kudos to the guys, Proton stopped that all. Yeah. Okay, let's go to the rumors. I'm good at time, hey. Let's go to the rumors. First of all, iOS backdoors. We have to say iOS backdoors are not hard to do, and I guess in about 10 slides you will see why. I met actually people that claim to have done it, and I do not doubt it because it is easy. The only thing you have to do is patch the image and adjust the simple once complement checksum. So in case someone is asking you, are there iOS backdoors? I guess there are tons of those. They're just not published. So be sure that you get the right image and not some friend passing you on an image and you're totally surprised what this listening port 31337 is. The next rumor thing, the big rumor thing, Bgp Hack Tools. I guess a bunch of you guys have heard about ADM BGP. I still have to see it, but people that I actually trust told me it works, and I'm not supposed to like ask for it. Apparently it exists. Apparently it works quite well. I have seen networks appearing and disappearing in the BGP routing tables. And of course, well, if you work anywhere on a provider, or you do a penetration test on a provider, or you do a penetration test on a provider without having a contract, you can do man-in-the-middle attacks. That is still easy. NSA backdoors, there are rumors about NSA backdoors in iOS. Well, with this piece of code, you don't need any backdoors. So if the NSA ever had the source code, and I guess they got ways to get it, I'm entirely sure that they got a list of bugs to exploit that is bigger than the actual source code number of lines. Impact in the past. Now the question is, how big was the whole stuff? Was it all just, well, easy going, or was it really critical? Now the thing is, easy denial service conditions are frequently exploited. You all have heard that there are people commonly referred to as script kiddies. Some of them actually exist, and some of them actually are able to compile complicated programs like lamb.c and will deny service providers or IRC networks or whatever. So this was quite frequently exploited. The death on arrival bug, we're going to talk about that in a few minutes, is the one coming out like, was it 2 weeks ago, 3 weeks ago? Something along those lines. Some people say it's the IPv4 bug, which is kind of funny. This was actually quite limited in exploitation. Why? Because Cisco understood that, hey, we're providing half of the internet infrastructure. We're actually doing advertisements on it. So we better tell the backbone providers up front that there's a problem and they should actually filter out this and that type of packet. But vulnerable routers will be around for quite a while. Guess why? Because the backbones did filtering. So script kiddie at home couldn't deny service like bigcompany.com. But if you're sitting somewhere near bigcompany.com and you're not running across a backbone, you can still deny service their routers. The HTTP exit level bug, as I said, is widely exploited, no matter what they tell you. Stores and routers got owned so badly, also switches and pretty much everything else that was vulnerable. Guess what? Nobody noticed. So, the present, did it get any better? Did they fix the stuff? On the topic of fixing, this is a router we found on the internet. I guess it's hard to read, so I'm going to tell you. This is a live router found on the internet by the guy with a nice decoration on his head here. It is running 9 series iOS, like iOS 9 something, 9.14 actually. This is not even available on the Cisco FTP server anymore. It's like, well, this is a live museum. I was thinking about this 9 series iOS something like Novell. You keep it running and just like put it behind a wall. Okay, latest iOS bugs. Stuff that happened not too long ago. SAA wasn't really big. I guess nobody except for a few crazy German guys interested in hacking Cisco were really like noticing it. It's a single packet denial service, of course, again, UDP, so you can easily spoof it. And what they did was they said, yeah, there's a problem with that, here's the patched software, here's the workaround, go do it. Never release details, as they, well, keep doing for every advisory they did. Of course, times changed, so in case you're interested, the line that says data, send this to the Cisco router, UDP port 1967, it will die. Now the death on arrival bug. This is kind of funny because it also tells you a story about the security community. As I said, it was made sure by Cisco that the big providers are informed up front and they're going to patch their backbones or at least implement access control lists, so for packets floating around their backbone are not allowed to exploit the bug. The thing here is, a lot of people were actually discussing on mailing lists if this bug is exploitable or not. Some people posted IRC logs of third person, that there is an exploit. Some of you might actually read full disclosure. It was kind of interesting because like a bunch of security companies contacted us and asked if we actually had an exploit for it. Now, my question is, if you're stuck in traffic jam, does that mean you control the traffic light? This is just a queue filling bug. You fill the queue with packets, and the bug is nobody's taken them off the queue. How are you going to exploit that? People, when you start thinking about, like, is a bug exploitable or not, this one is definitely not. Period. Well, most of the security companies didn't actually understand, and so I still get emails to this respect. Just security notices, stuff that happened in, I guess, the last 2 years or something, that happen to be security notices and not security advisories. Security notices, to tell you the difference, is they assign the status of a security notice to everything they don't want to have spread around to all the customers right away. So what they do is they put it on the website and just shut up. Okay, here are the notices. CDP, router denies service. Enhanced IGP, router aided network-wide denial service. TFTP long finding buffer overflow. Well, exploited, as you might know. OSPF buffer overflow. Udp Echo Service memory leak. We will talk about that in a minute. And HTTP 2 GB request buffer overflow. We will cover that one as well. Short review on stuff some of you might not have catched the totally boring heap exploitation on Cisco IOS talks. This is the short version. What we have in a Cisco is basically two types of memory. They're both heap memory. In theory, they're both RAM-based. We got what they call main memory, which is block-based, as you know from Linux, Windows, whatever. And we got I/O memory, which is fixed size blocks used for forwarding packets directly assigned to interfaces and routing processes to speed up the size. So I/O memory is same size, main memory various sizes. It is all based on a tree structure, which I know now for sure, and every single block is basically part of a linked list. So they got like linked lists of blocks in general, what we can see here on the left side. And they also got linked lists for caching purposes on interface buffers. They got linked lists of free buffers and all kinds of stuff. So I/O memory is a bit more complicated actually because it's dynamically scaled linked lists of fixed size buffers. What they do is for every single interface, you got a so-called private interface pool. It's just a bunch of memory areas, memory buffers that are exactly the size of the NTU. So everything you receive on the interface or send on the interface will for sure fit in this buffer. It's just a matter of speed, so you're not like malloc every time a packet comes in, which is going to take time. And it's important for specialized buffers and forwarding systems where the main CPU does not touch the packet, but you actually have the interfaces dealing with the whole thing. So the main CPU basically tells everyone, if you receive something for this and that destination, send it right over to this interface, don't bother me with that. Public buffer pools is basically for whatever happens to show up in the memory, like defragmentation of packets, smaller routing table updates, stuff like that. And they're in all kinds of different sizes, like pretty much like the t-shirt, small, medium, large, extra large, tent, whatever. And the allocation on I/O memory is not so frequent as with main memory. What you get is you have the pre-allocated stuff every time an interface is put active. And then you got thresholds, top and bottom thresholds, and if they're exceeded, you allocate memory where you do not. Okay, so how does a memory block look like? Some of you might seen the Frag article on heap exploitation in Linux. And remember that they got like, what is it, about 8 bytes per memory block header overhead. So here we got 40 bytes. In case you wonder why you need so much memory every time you upgrade your iOS, this is the answer. This is like one of those blocks is 32-bit wide. Pretty much none of it is used. We just got like magic numbers that are static, magic numbers at the end that are static, which actually order to the next magic number at the beginning of the next block that's static, so you basically waste 8 bytes. You got the process ID allocating the block, you got the address, actually you got a 32-byte block in the memory header as a canary. Nobody uses it, so they have the canary in there, it's not used, great. We got pointers who allocated this in terms of process, we got pointers who allocated this in terms of like exact address of the call to alloc. We got the next to the previous pointer for linked lists, we got a size, we got a reference count that is redundant with the size, so all we actually need is about 12 bytes and all we got is 40. Theory of heap overflows, I'm doing that quite quick here. You got a block over there, the host block, that contains the data you're sending in, and well, you can overflow this block. You got the next block, and it got a block header as well. So what you do is basically overflow the first block, overwrite the header of the next block, and since there are different situations where the first block actually gets cleared and totally data erased, overwritten with OD, you have to send the actual shellcode behind that. The free on iOS is quite useful. You see the lines here? I guess not. It's too dark. I'm sorry. Yeah, it's still linked list stuff. The free on iOS actually uses a different linked list. You got the linked list you just saw with the next and the previous pointers. And so here pointer exchange takes place. So you overwrite one of the pointers or two of the pointers, and they're used in a pointer exchange. Not visible down there. Oh shit, I'm sorry. You got a pointer exchange taking place where the previous pointers actually point to not the block before them, but the block before them. And the same for the next pointers. You basically take the middle block out of the chain. This is done by pointer exchange. So you got arbitrary memory right here. The problem, oh, those are visible, yeah. The problem with that is that one of the two pointers is really closely evaluated, and there is only one correct answer for it. So it's a pain in the ass to figure that out. Arbitrary memory right, therefore, has to use different pointers. The other pointers we got is for free memory blocks. The stuff that's red over here is the 40 byte we already wasted. Now we got some more to waste. And then finally at the end we got two other pointers, free next and free previous. They're used for the linked list of free blocks. Those are not validated, so we can put whatever we want in there and still have a pointer exchange taking place when free blocks are co-escalated, merged together to make one big free block. This is the time we can actually do arbitrary memory writes. But the problem here is those are heap overflows, which means they're not so stable as stack-based overflows in general. We need tons of information on the device already. We need the previous pointer. As I said, there's only one correct answer for a 32-bit pointer. It's pretty much like a key for the attacker. For I/O-based memory overflows, you actually need the size of the memory. You need to know where you are in memory. Then you need, for actually executing code, you need an address in the code space that you can jump to. And then, of course, you need an address where you're writing your jump information to. What we did was we were writing them in the process information, basically like a save task information block, writing it to the next instruction or return instruction address in the stack. So you need this address, and of course you need to know where your code is, which is a pain in the ass, and reliable remote exploitation is not possible with that. we found a small bug. It's really totally trivial and nobody really cared about it. It's in Cisco iOS 11 series. There is the Udp Echo Service. Now, Nessus tells you for ages that Udp Echo is bad because people can do ping pong with that. You can do a lot of more pong than ping with it. What happens is you send a Udp Echo request to this port, and you say in the Udp header that the packet was about 10K long. You only send 1 byte with it. The device is going to answer with 10K of information out of the memory. Well, guess what? It's I/O memory. It's the memory used for packet forwarding. And so you actually get data structures out of the memory, and now you can look into the actual memory right now working on the system. And well, if you increase the number and increase it more and more and more, you get 19 kilobytes memory for 1 byte payload of your Udp Echo packet you send there, which is quite a good number. Actually, I just realized you can use that as a DDoS vector. Anyway, and comparable bug in this happened to be in 12 series iOS with the Cisco Express forwarding, yet another forwarding technology they developed. With IP header length. You had an IP packet that was really short. The header said it was 14K. And so it would forward 40K instead of the short packet. Now what we can do with the leaked I/O memory is reliable remote fingerprinting. We got the block headers. We got information on who allocated them. We got the address of the allocating function and all this stuff, and we also got information on which memory it is residing on based on the next and previous pointers. Now those numbers are specific either to platform or to iOS image. So all we have to do is match the numbers and see what platform it is running on and what iOS image, and this is 100% reliable. So this is what we get in detail. Oh, I'm glad you can see that. This is like the echo data we get back. This is 1 byte, whatever A we send. And then we get the different receive buffers, because in the buffer where the echo request packet was residing, this is an I/O buffer. So next to it is the next packet buffer, next to it is the next packet buffer, and since it's a ring buffer system, you actually get all the packets in one straight memory region. So we get all this data. One of those blocks actually contains the already known block header, plus the ring buffer content, of course, and the red zone. So all those pointers are available. We got image specific, platform specific, and we actually got the Ethernet packet. So if you wonder, yes you can. Here's the remote sniffer for iOS. The leaked memory contains the packets. So all you have to do is take the memory, parse it out, find out what the memory blocks are, find the packet offset in there, and do some kind of TCP dump comparable decoding. And all you need now is a piece of software sitting on your laptop, downloadable from our website, pointed to the right Cisco router, have a Udp Echo Service running, and sniff what's coming in there. The good news here is, first of all, the tool is available. Second, this is how it looks like. The good news is it's the receive buffer. So what does a router receive if someone's trying to manage it? First line it will receive. It's probably the password. Second line it will receive. It's probably the enable command. Third line it will receive. Guess what? The enable password. On another note here, people are saying CDP is bad. We know that, but we're a provider and we've got a bunch of Windows coders and we have no idea how to manage Cisco's. So CDP is great because we find the other devices. And while it's layer 2, so nothing can happen, guess what? You see the CDP as well, because it's in a receive buffer. But of course, there are more bugs. iOS HTTP bug. As I said, almost all embedded HTTP implementations are shit. This one is no exception. We found an integer bug in iOS. It's silly to trigger, I have to admit that, but it's fun. It's iOS 11 and 12 up to 12.2 whatever latest, and it requires you to send a 2 gigabytes URL. What happens is they count independently how big the buffer is and how much data they got. So what they do is, they count how much data they got and see if it still fits into the buffer, which is a signed comparison in assembly. Easy to find in assembly code. Took them about 2 weeks to find it in the source code. The thing is, they continue counting how much data they got when the buffer is already full. So instead of like tearing down the connection or whatever, they keep counting, and just keep throwing away the data they got. Well, after they counted to 2 gigabytes, they flip over. And of course, then you got a negative minus whatever gigabyte received number, which is smaller than the buffer size, so it gets copied into. Welcome, you got a Stack Overflow. Now we have Udp Echo Memory we just discussed, so we see attacker provided binary data, we see live iOS memory, and we have the ability to fill all the ring buffers by sending not one echo request, but like several of them. And we got the HTTP overflow, that is textbook, frame pointer, and return address overflow. So what we do is like, we put them together, cook them, and like spice them a bit, and see if an exploit comes out of it. So what we do, send full binary shellcode on the Udp Echo. Use the Udp Echo to calculate the code address. Actually, the address the code is in, because we see it in the answer. We select the shellcode address that is most unlikely to modify, because it's a ring buffer, and if it's a Cisco router not sitting in the Phenonet labs, but actually out there somewhere, it got other things to do than getting exploited, so it's actually forwarding packets. Those end up in the ring buffers as well, so we have to make an intelligent decision on which address we're using. And then we basically terminate the exploitation, overwrite the return address with the already known address for our shellcode and on the box. I'm going to skip that, that's what I just said. Okay, in color. Here it is, HTTP connect. Send 2 gigabytes of A. It's going to take a while. Actually, with a 100 megabit Ethernet connection, it takes less than an hour, so it's feasible. Send the shellcode in Udp Echo. Get the answers back, repeat until happy. Send the overflow, and open the box. Binary HTTP. Problem here, of course, is some characters are not good in HTTP. Obviously, line feeds and character terms are bad. 0 characters are bad. But HTTP encoding is supported by iOS, and we figured out it's actually the same buffer before it returns off the function. Thank you. It's totally easy. We just put the address HTTP encoded in there, and we'll end up exactly how we want. Return address selection, as I said, you have to make an intelligent decision, so to not grab like your neighbor's instant messenger packet as shellcode. There are different ways to do that. The strategies we tested all had different values. You can see them here. I'll look them up later. Just let me tell you, the lowest memory location plus like 1 or 2 for grace is the best way. This buffer is so seldom modified that you can have a shellcode sitting there for about hours. Now we figured what we did with the overflows was shellcodes that replaced the whole config. It's nice, but it's not considered really cool. So what we figured is we should actually go and research the binary of iOS and find out how it actually works. And it turned out to be totally simple. You got the raw monitor. The raw monitor actually has debug capabilities. You can set breakpoints, you can do disassembly, whatever you want. It's pretty much like your MS-DOS debug exe program. And the identification of which code is actually responsible for what you're trying to achieve is also simple, because this being an A out image, you have the strings that the function is using sitting right in front of the function in the text string. So the only thing you need is turn on all possible debugging, see how this one message you're looking for is calling by, and then go to the image, look for the message, and, well, you've got the function right next to it. So what we're doing with that is what we call next generation shellcode. What we do is, instead of overriding the configuration, we do runtime iOS patching. We patch elements in the iOS that are considered annoying, which means this is iOS text segment checksum function that goes ahead every 30 seconds and tries to figure out if the text segment means the code running is still fine. Well, we can get rid of that one. Then we got rid of the more interesting portions, especially the ones that do this annoying password validation stuff. So we disable VTI authentication entirely, and we actually disable the verification of the enabled password as well. For that to work, we need to keep iOS running. To keep iOS running, instead of crashing the whole thingy, we have to make sure that the overflow actually does not destroy too much data, which is not possible in this case because we've got HTTP encoding. The Motorola call structure on the other side actually has the big advantage that it saves the stack pointers and frame pointers pretty much like the infrastructure does, which I didn't know before. But it is possible to search the stack upwards for return address of the major calling function, find out if this is supposed to return true or false, return whatever is needed to make it happy, and then do the clean return. This is the code for that. It's quite easy. You see the downfall here is actually this compare line over here, because you need a memory address for the return call. So this is again image dependent. And you just loop backwards through it and then do a clean return. Advantages, of course, the router stays online, it doesn't crash, and doesn't make your HP OpenView go ah! And so the configuration is preserved, which is a good thing, because, well, people tend to use different passwords in all different routers they got, and they have all different passwords for all different routing processes, and never use the same access lists on different routers and stuff. So configuration preserving is pretty good. And of course, finally, it's kind of like an ego thing, but we actually proved you can do runtime iOS backdoors. Disadvantages. Big disadvantage, it's image dependent. You need a large target list, obviously, for all the different images out there. And you still got this annoying checksum error message on the console, if anyone bothers to look at it. So this is the exploit. As of yesterday evening, you can actually download it from the site. Effectively, it's a reliable remote iOS exploitation, of which I'm partially proud of. There is the address calculation we just discussed with the Udp Echo info leak. We got the address selection strategy sorted out, and we patched iOS. And this is how it looks like. You don't have to do anything except for sending 2 gigabytes and wait a while. But here's a different approach. It shouldn't be image dependent. Shellcode shouldn't be image independent. So modifying iOS code base is image dependent. Otherwise, you're supposed to write a reverse assembly shellcode that like finds the function, stuff like that. I leave that to TISA. Modifying iOS configuration is not image dependent. So all we need to do is have a shellcode that runtime modifies the configuration, and all we need for that is an str function, a memcopy function, and a checksum function to fix the damn NVRAM. Well, we can do that. So what we actually did was another shellcode that would find the beginning of the configuration in the NVRAM, then find occurrences of interesting strings, in this case password and enable, replace those occurrences and especially the data afterwards with whatever data you provide, and hereby replace the authentication information for console passwords, VTI line passwords, enable secrets, whatnot. Recalculate the checksum, write it back into NVRAM, reboot, you're done. This is how that looks like. You might actually see the 2 absolutely screwed lines down here. This is because we just replaced the password and put a line feed in it. Why? Because if iOS sees crap while moving and reading a configuration, it will just say, this is crap, I'm ignoring it. We're fine with that. So we don't have to like shift text around and stuff. Advantages of that. Of course, it's image independent. The only dependence we still got is the CPU. Well, I do not think we can get rid of that, except for like multi-platform shellcodes for Motorola, PowerPC, and MIPS. If you come up with that, you're invited to CCC's challenge next year, I guess. the configuration is pretty much preserved. We can actually use the same shortcut with a small modification to copy the old passwords to somewhere else in NVRAM and like make them a command in the code line or whatever. And yeah, you got more choices of what to do. You can reconfigure the router instead of replacing the configuration. Disadvantages, as I said, it's still depending on a CPU, and the router has to reboot once, so network management is going a bit all over you. So what? The thing is, the community at large actually gains experience in playing around with Cisco. The responses on the death on the rifle bug were so happy that I noticed there is a slight change in like perception of what Cisco actually is. iOS still, up to today, has no internal protections. So if you got code to work on it, you basically got kernel level already. Features are added to the old code tree. They got several different attempts to rewrite the code, to make it better or totally like redo it. It never came out. They were still adding crap to the old one. iOS still copies data into buffers that are not large enough to hold it. Other people call that a buffer overflow. They still do that all over the place. And as a side note, there are other people doing iOS exploitation as well. The only difference is we do it in a public and talk to you at the camp. This is out of body of secrets. Most of you might know it. James Bamford. A quote by the Deputy Director of NSA talking about hiring people for hacking Ciscos. So, the future. I'm running out of time, but I want to talk to you about the future. Is it getting better? Most of the bugs discussed here are parsing related. Those guys can't parse for shit. There is absolutely nothing they ever parse reliably. And still in iOS, looking at the research, you see that every single process still does its own IP parsing. So, like, you have 99 processes doing IP parsing well, and like taking into account fragmentation and TCP options and whatnot, and you got this one single process doing it wrong. This is all you need. They do not have a central place for IP parsing. They do it like every single time. And see yourself, this is about, well, it's not exploitable, so I never bothered to tell anyone, but it's a good example of how good they do parsing. You send an HTTP request, get / and then you use like hexadecimal numbers, 32 bits. If you do HTTP debugging, the debug output tells you client version is 2 milliards what not, .-1. This is a good parsing. If this would have been a length field, they're screwed. So I figured with all those Microsoft developers starting as Cisco iOS coders at Cisco, they should actually do what all Microsoft people do, listen more to the mouse, and the mouse says, parse correctly. Okay, Outlook, not Microsoft. The death on arrival bug, the Q bug, was pretty bad. Because not it affected so many systems, but it was a design failure. The design failure being the processes are supposed to take packets off the queue. Now the queue is the one single resource in the router, and you've got lots of processes. So I'm entirely sure we will see more of those in the future. Of course, not all overflows are found yet. That would like kill my hobby. The complete rewrite, as I said, is in progress. Again, it's about the 5th time now. First question, when will it come? Second, will it be secure? Probably not. Third question, will it support loadable modules? People are talking about that for years now. So I guess it will support loadable modules. Now talk about a full shell on a router with like your own Cisco IOS model. Will it have third-party modules on it? I can just imagine people still way better in writing buffer overflowable code, supplying components to Cisco IOS. On the other hand, on a Cisco FTP server, we got over 22,000 different iOS images. They're all in production. They're not updated all the time. New versions come out like weekly, and as you have seen, who's bothering updating their routers? You might have seen this in TV advertisements. By the way, let me tell you about the self-securing networks. Do I got time? 1 minute? Okay. I tell you about the self-securing networks you see on German TV all the time. I talked to the Cisco guys, I found out what it is. It is a command supported at 3 platforms in the latest iOS version called auto-secure. Auto-secure does not secure your BMW. What it does is, it turns off the crap that it is not supposed to run in the first place. So it turns off HTTP server, it turns off UDP Echo, and all this crap, and this is what they call the auto-securing network. As you see, this is what's on TV, so we figured we're going to modify this a bit. And I guess that's pretty much it for now. Yeah, so I would say I'm open for questions. No questions, though. Oh, there's one.
Actually, pretty much all the software broken, so
It runs the internet. Quite honest, I'm actually living on like old Lucent equipment I got when I used to work for Lucent, but don't tell anyone, and I'm not going to tell you my IP address. Okay, so thanks a lot. And don't miss out FTR. After this, he's talking about more Java crap in embedded systems.